As you can see, I come from a very small, with respect to NIST, National Meteorological Institute, which is the Italian one and which is located in Torino. But I would like to it's a stupid saying, but I would like to say that the talk was for experimentalist as me working in magnetism. It's been an excellent one. And it has pointed out all the problems that we have banally in reading works or whatever, because the magnetic community is very resilient to change from the CGS to SI. And this is a problem, and more than it has to come is the problem of nanomagnetism, because we have standards, we have procedure to measure very big sheets or whatever, but working on powder, thin films, or even slower magnetic entities is a problem. The first round robin of measurements on VSM, which is a very standard procedures, gives results very spread. And if you work as Ron pointed out in a meteorological institute, this is quite astonishing. Anyhow, so I would like to express my deep thanks. This is just to say this to Ron, because it was really very, let's say, inspiring and clarifying, because it's not that easy to move in this world. So just to be brief, this work is on magnetic ferrites that are very much known from decades and used. And I would like simply to highlight the fact that they can be exploited both in electromagnetic ones, but their hysteresis loops has to be measured with accuracy. I will, this is while they are, let's say, while they are so tunable, because depending on, they are basically, ferrites are iron oxide that are doped with other elements. Depending on the element, you can get different microstructure. That is as it is well known, the microstructure determines the magnetic properties. So if you deal with a spinel structure as it's seen on the left of my screen, you typically get soft magnetic properties. But if you have an hexagonal lattice, you can get hard magnetic properties, and this can be changed simply by changing the discomposition of the iron oxide. Let's talk. I will talk of spinel. Of the results we have obtained on spinal ferrite structure, and this is the lattice, a cartoon showing the lattice that is typically of spinal ferrites. You have the tetrahedral side and the octahedral side, and then the depending on where you place it, you can get different properties. While we use ferrite powders, because mostly because they have a very low cost. They can be prepared very simple chemically. They are stable, and as I said, as I told you, they be very much tunable, and then they can have, being iron oxide, high biocompatibility. It's not moving anymore. Why? Okay. This gives you leads you to a wide variety of application in many fields, as catalysis, biomedical, also electronic device. They can use for remediation of water, and the most important magnetic properties are the hypermobility in the radio frequency region. They have high electrical resistivity, which leads to very low hysteresis losses, because there is eddy currents are limited in these materials. Then they have a high mechanical hardness and a very high chemical stability. Let me show this concerning the magnetic losses. You see that this is the core system on some soft, very well-known soft magnetic properties. And you can see that we can go from iron powder, where you have very high losses and not much saturation, magnetization, flux density. And you can see here the amorphous one are located here, but the ferrite are immediately here. They have a low core losses and they have quite high, let's say, saturation flux density. But let's say that from amorphous and ferrite, the balance should be more or less the same. So you can save energy, and that leads to this CO2 reduction, and they are in a very high saturation density, which is not the case here, but they are mainly powder. You can go to very high miniaturization possibility. Here we have our try. We have worked with cobalt, lithium, zinc mixed ferrite powders that can be exploited for both magnetic hyperthermia or drug delivery. And then I will briefly show some new tries that we have made in collaboration with Torino Politecnico of 3D printing with randomly dispersed magnetite, commercially available magnetite powders. And this can be exploited as a micro nano robots in the body. This is very well known. I will go, because I have 15 minutes, I will go, and I speak a lot already. These are the main application of magnetic nanoparticles in diagnosis, as in magnetic resonance imaging, in drug delivery, in lag-on-chip, in hyperthermia, that will be the subject of this work, because we measure the magnetic hysteresis loop. So the contribution to magnetic hyperthermia due to magnetic, the magnetic, obviously discarding the motion. Here our ferrites with our decomposition are positioned at two different crystallographic sites, and then the location of both positions can be both tetrahedrally or octahedrally coordinated to the oxygen atoms. We are working with cobalt ions that are that can provide the high value of heat release, because they are known to have a strong magnetocrystalline anisotropy, although a moderate magnetization. The non-magnetic lithium ions are been chosen because they have low toxicity, and the other non-magnetic ion is exploited because it substitute the magnetic divalent ions and allow the tuning of the magnetic properties. We have prepared these samples by Sol-Gel autocombustion. Here are the composition. Why we have used these? Because it's an off equilibrium technique, and these can different cation distribution, and hopefully different magnetic properties. The cobalt composite, the cobalt zinc ferrites does not need any further maltreatment, but while the lithium ferrites, yes, it has to be treated at this temperature. Okay, the main parameters that influence the magnetic properties are obviously the microstructure that gives that leads to changing in saturation magnetization in all the magnetic properties interesting for application. These XRD simply show you that these are our composition are all Spinel 1. The lattice parameter increases with increasing zinc content because it has a higher radius, so simply, and all are nanocrystalline. This is the microstructure, which is very nice to be seen because the explosion techniques leads to a beehive microstructure, and this is because there are a lot of gases that are generated from gels during the drying process. These are the EDX and the silicon. The silicon signal is the one that comes from the substrate in which the powder has been dispersed. Here I come to the magnetic properties. We have calculated a specific absorption rate by means of hysteresis loop in two conditions. The static one by VSM. We have worked with the same field amplitude as this as the magnetic hyperthermia setup. And here is the dynamical loop tracer that work at this frequency, and we have worked on the very same sample in these two cases. However, this happens everywhere. We have made these measurements on dry particles because making these measurements in liquid, disperses in liquid, as the magnetic hyperthermia is not that easy, and the two are not comparable. These are the two important parameter in magnetic hyperthermia. And that here is the heat release, the power release, that in our case is the one by the magnetic particles when submitted to an IC magnetic field. And this has been calculated by the area of the hysteresis loop. Another important parameter is the intrinsic gloss power, that is the SAR over the frequency at which the measurement is made, and the applied vertex field. Here are the results of our measurements. This is one composition, as obviously can be guessed by increasing the magnetic field. The area of the hysteresis loop is higher. It is shown the losses, how they have been calculated as a function of zinc constant. You can see that the zinc having 0.5 is not monotonic, as the highest, given that it has the highest magnetization saturation, it has a higher losses. And conversely, the zinc that has the higher, the 0.08, that has the highest coercivity, is seen that their losses are seen here in this region, in the low losses region. Here are the dynamic hysteresis losses made at 69 kilohertz. Again, here are the behavior with increasing the field of the cobalt 52 zinc 44 composition, and here is the behavior of the zinc content, and the zinc 0.48 is the one that has the highest losses, so it can heat more, it can release more heat. We have always think that here the contribution of eddy currents may not so negligible because of these non-monotonic results. This is very quickly the hyperthermia setup. We measure, as you see, in liquid. We have a tube where we hold the liquid. We have a coil, a big coil for generate the radio frequency electromagnetic field, and we have a thermometer for measuring the sample temperature. Here is a typical results of our temperature. We have a temperature rise and we measure it for about 1 hour. Then we leave the sample we record also at the point that we switch off the fields, and we record also the decay, the temperature decay towards room temperature. Here is the SLP is 150 watt per gram, and this is the field at which we have measured. Our setup is we have tried to model it in order to take care of all the dispersion towards the environment that we have by simply using a calorimetric equation. Here is the comparison with the static hysteresis losses that we have on our zinc ferrite, little zinc and cobalt zinc ferrites, and these are the results of our hysteresis loop, and you can see that there is a very different behavior for all the three composition, but the cobalt zinc, but the zinc ferrite is the one that you see that has a lower hysteresis loop area, as is seen there. These are the SLP. This is interesting because it is the specific low power measured or calculated by the tree technique. We have the AC loop, the thermometric measurements, and of these nickel zinc ferrites. These are the ones that has been measured with the thermometric ones are measured in the hyperthermia setup, while these are the contribution measured with the conventional hysteresis that I've shown you before. And you can see that there is the thermometric measurements possibly take into account also other kind of losses, of thermal losses, as in. I think that I made more my time. Anyhow, I will briefly show you the idea that is under using another kind of very simple ferrite, which is the magnetite, for magnetic actuation by simply dispersing the magnetic nanoparticles in polymers, and then making a 3D printing in order to prototype some robot. This work has been done using two types of polymer. One is one gives rise to a rigid matrix in which the nanoparticles are dispersed, and here are the one of the soft matrix. And you can see that there are many different possibilities of playing with shape and whatever. What is crucial from the magnetic point of view? Everything, because it depends on the homogeneity of the dispersion, the fact that you can apply the magnetic field and you can create chain inside of inside of your matrix. And this, if you deal with homogeneously dispersed, your material results to be magnetically isotropic, and all the three directions that are shown here are magnetically equivalent because they lead to the same hysteresis behavior. While if you deal with chain, you have a magnetic and isotropic materials, and the samples can be easily magnetized on the along the magnetic chain direction. With this, I would like to conclude, and I would like to thank you for your kind attention.